A decision tree for a product development example is shown, and we want to see how we can use Bayes' theorem to update prior probabilities or outdated probabilities on decision tree. By that I mean these two probabilities mentioned here for high demand and weak demand for the product that are outdated or prior, and we want to get to the posterior or revised version of them for the other branches of decision tree. So with that in mind, let's start from the project definition and problem definition. So decision node number one, either we are bidding on a project or not. If we do not bid, we're not spending anything, therefore the payoff is zero. Let's say if the payoff or profit in millions of dollars are supposed to be reported as the leaves of the decision tree. And if we bid, then there is a cost of $200,000 to just prepare the bid for the project, so we have to spend that much money. After we bid, we get to a chance node number two that the outcome of the chance node is beyond our control, so there is a 75% chance that we win the contract and we can start the project or the product development, and there is a 25% chance that we lose it. If we lose it, there is nothing we can do, which is a 25% chance with a probability of 0.25, and then we end up just having spent $200,000 and getting nothing. So it would be negative $0.2 million. So it's a $0.2 million loss. Now, if we win, which is with a chance of 75%, then we have to invest $3 million in product development to get to decision node number three. So by the time we get to decision node number three, we have spent $3 million in product development and $200,000 in bidding. So at decision node number three, either we do a no market research, we don't do market research, or we do a market research. But if we want to do market research, we have to pay $100,000 for that. So let's look at the no market research scenario. So we get to a decision node number 7, and we have the option or alternative decisions to either build the product directly ourselves or sell their IP rights or patent to somebody else. Let's say if we sell the patents or IP right, then let's say in that process we're going to get, let's say, $4 million for patents. And since we are getting $4 million for patents, but we have spent already $3 million in investment and $200,000 for bidding, so the outcome will be the output of as a leaf of this branch would be 4 minus 3 minus 0.2, so effectively is plus $0.8 million gain that we're gonna get in this scenario. Okay, so if we sell patent, is always $4 million for selling a patent. Alright, so if we build a product here, then we will get it to a chance node number 10, and chance node number 10 with a 60% chance we're gonna have a high demand or high and good economy, and let's say in that scenario we're gonna get $6 million in revenue. And if that is the case, then 6 minus 3 minus 0.2 will get us to $2.8 million profit. And if the demand is weak, let's say in that scenario, we're going to get only, let's say, as an example, $4.5 million in profit, in revenue, and then let's say 4.2 just to make it easy. So $4.2 million in revenue, but 4.2 minus 3 minus $200,000 gonna get us to 1 in terms of $1 million in payoff for profit. Now, if we go to upper branch here, meaning we do market research, then let's say we get to chance node number 4, and at chance node number 4, 2 states of nature come out that are beyond our control. Either the market research result will be forecasting a strong economy or weak economy, and if it is a strong economy, we get to decision node number 5. Either we build a product or we sell it. If we sell, again we get 4 million, but since we already spent $100,000 in that case, then it would be 4 minus $3 million minus 100,000 minus 200,000. So we're gonna get 0.7 million in payoff profit if we sell the IP at this point. And if it is building the product the decision is building product, but then we get to a chance node number 8, depending on the real situation with the actual demand. Then we get high demand, as we said before. As a result of high demand, we're going to get $6 million, but then again, we have already spent $3 million, 100,000, 200,000, so we are going to get $2.7 million in payoff. And if it is weak demand, it was mentioned that it would be 4.2, and then it will be 0.9. Okay, so the same thing will be for the bottom branch. So if it is forecast weak, we'll get to a decision node number 6, and then we will make a decision whether we build or sell the IP. But we have spent already 3 million, 100,000, 200,000, so naturally we're going to get either 0.7 or 0.9 or 2.7. So these are the payoff numbers at the end of the decision tree as leaves of the decision tree. And now we are supposed to just compute the probabilities. Okay, so let me highlight what I mean by that. 0.6 and 0.4 here are the probabilities of high demand and weak demand, as prior probabilities were outdated ones. The market research information is sort of highlighted on top. So if we pay for market research, what we get will be a prediction or forecast of whether it's forecasted that the economy is strong or weak. And also, market research is telling us about that it has this information that the probability of forecasting a strong given that economies the demand is actually high is 0.8, and the probability of forecasting a strong given that the demand is weak is 0.3. So these are the information that they come with the market research. So let's use them. At this point, let me highlight with a good color. So at this point, what I'm interested in is the probability of high demand given weak forecast. So what I am interested in is the probability of high demand. So let's say high demand given weak forecast. Okay, so I don't have it. So how can I find it? Well, this is the part we're going to use Bayes theorem. So it is equal to, this is a conditional probability. So you know that it is probability of high demand. So we can rewrite it in this format, right? The formula for conditional probability is this one. Joint probability of high demand and weak forecast divided by the probability of weak forecast, which we don't have it, by the way, equal to, and then we can rewrite the joint probability using multiplication law, and it will be probability of a weak forecast given high demand times the probability of high demand, divided by, of course, probability of weak forecast. Now, the probability of weak forecast given high demand is available because the report comes back with this information. It says probability of a strong forecast given high demand is 0.8. Therefore, the complement of that, the probability of weak forecast given high demand is 1 minus 0.8, which is 0.2. So we have this information. That's good. And we also have the probability of high demand. That is basically this unconditional prior outdated probability. So we have all the information in numerator. What we don't have is, so basically let me write it. I'm going to use a different color so that it's highlighted. The first one here is 0.2 and the second one here is 0.6. What we don't have is denominator, but effectively we have that one as well too. I mean, we can write it this way. Probability of, so I'm just going to focus on denominator. Probability of so the probability of weak forecast is the probability of weak forecast and let's say high demand plus the probability of weak forecast and low demand. I mean, because high demand and low demand are the only possible situation, and they are when we consider both of them, they are taking into account all possible scenarios. Okay, so what we have is the probability of weak forecast given high demand and the probability of high demand. That's for the first one. And the second one is the probability of weak forecast given low demand times the probability of low demand. Okay, so this first one here is what? Weak forecast given high demand is, as you saw above, is 0.2. This one here is the unconditional that you see here, 0.6. And this one, weak forecast given low demand. Again, the same thing. You have the strong forecast given low demand, which is 0.3. So probability of weak forecast given weak demand, which is low demand, would be 1 minus 0.3 is 0.7. So this one is 0.7, and the probability of low demand is unconditional or outdated probability here given to us is 0.4. So when we have these numbers, 0.2 times 0.6 is 0.12, and then the other one is 0.28, and so you get 0.4. Very nice. That is the probability of weak forecast. So I'm going to write it here actually. The probability of weak forecast is 0.4 as computed here. Naturally, because we either get the weak forecast or a strong forecast, so if the probability of weak forecast for the market research is 0.4, you can conclude that the probability of a strong forecast is 0.6, 1 minus 0.4. So we have these two numbers. That's very good. Okay, and also we are now able to find the probability of high demand given weak forecast, because it effectively is 0.2, 0.6 in numerator, so 0.12, and denominator we just found it is 0.4. So it's 12 over 40, and therefore it is just 0.3. So we found it. So we're gonna write this is the probability of high demand given weak forecast. So we are effectively, we are in weak forecast, and we are going to high demand. So what I'm gonna write, I am going to write here under this branch, I'm going to write 0.3. Maybe with a different color so that it is clear I'm talking about the probabilities. Maybe I use blue color here, so it will be 0.3. Okay, now the other one is probability of weak demand given forecast week. Of course it would be complement of that, which is 0.7. Now we just need to do one more computation in terms of using Bayes theorem like we did, but this time we need to do it for the forecast as strong to find the probability of high demand with the forecast as strong. So I just need to repeat this exercise one last time, and it would be, let me see if okay, great. So it would be probability of high demand given a strong forecast. Same procedure, so it would be probability of high demand and a strong forecast, or basically probability of a strong forecast given high demand, and times P of high demand divided by P of strong forecast, which we already found just moments ago. So you can just substitute for these things. You can just substitute for these things. So probability of a strong forecast given high demand is already supplied by the market research. As you can see, it is here. So it is 0.8. And the probability of high demand is what we saw in the outdated or unconditional initial values or prior probabilities, which is 0.6, and denominator is probability of strong forecast. We already found it is 0.6 as well. So what is the outcome? 0.8 times 0.6 divided by 0.6, so 0.8. Very nice. So we just found that this is 0.8 written right below the top branch, the probability of high demand under strong forecast scenario, and naturally weak demand in that case is just complement of that, which is 0.2. So all I'm trying to say is, using Bayes theorem, we managed to find updated or revised probabilities under the scenarios that we pay for market research, and it comes back and report to us forecast is strong or forecast weak. So therefore now we are able to proceed with respect to the rest of the questions. Okay, so now that we have all the probabilities on this decision tree, we are able to continue and use the backward pass-through method, starting from the right side in decision tree, and from, let's say, chance nodes 8, 9, and 10. We find their expected values and continue so that we select the decision that maximizes our expected value, because we're using expected value approach. Okay, so what I'm going to do is this process. I am going to say, okay, expected value of node 8 on top, very top. So I am going to highlight it again. Node 8 is here on top on the branch. So expected value of node 8 is equal to, so we're going to multiply 0.8 by 2.7, 0.8 times 2.7 profit, plus we're going to multiply 0.2 by 0.9, so 0.2 by 0.9. So the outcome is okay. So the outcome is going to be 1.6. Then it's going to be 2 point. I'm just trying to make sure I'm not making a mistake. 2.17. 2.16. So 2.16, and then the other one is 0.18. So we add up these two numbers, we're gonna get 2.34 million dollars. So expected value of node 8 is $2.34 million. I'm going to write it on node 8. So here we have $2.34 million, right, written beside node 8. Okay, we can do the same thing for the rest of the nodes. For example, you can do, let's say, expected value of node 9, the chance node right below the node 8. So same procedure, 0.3 is the probability times 2.7 times 2.7, and then you have 0.7 times 0.9. So what are we gonna get? Okay, this time we will have this number. So we will have 0.81 plus 0.63. So the sum will be 1.44. So I'm going to write it right beside node 9, $1.44 million. But let's go back to node 8. Let's look at decision node number 5. So what's going on? If I build the product, on average, I expect to get $2.34 million in profit. If I sell the IP, I am going to get 0.7. So forgetting about the risk, which is associated with the standard deviation or variance of these outcomes, just looking at the average expected value, it's obvious that I have to proceed with building the product, because I am going to get on average 2.37 million, which is considerably higher than 0.7. So therefore, the decision at node 5, this is the process of backward pass-through. As you can see, we started from the right side of decision tree. We are doing backward pass-through. We are going backward through the decision tree. So I'm going to write 2.34 here because effectively what I did is I'm saying expected value at node. So I am saying expected value at node 5, decision node, is effectively maximum of expected value of node 8, which is $2.34 million, and 0.7 million, which is the outcome of the selling IPO. Obviously, it's expected value of node 8, which is passing through backward, and it is $2.34 million. So that's why I wrote 2.34 on 5. Now, if we get to node 5, basically whenever we pay for market research and we get this forecast is strong, the decision will be build a product, and that's it. 2.34 we're going to get on average. You can proceed with this process also for this chance node 9 and then decision node number 6. For the same reason, with the same process, you can see that if I build the product, I'm going to get on average 1.44 as expected value versus the 0.7 that is the result of selling the IP. So again, the decision is build the product. So I'm going to do the building the product. So there you go. This check mark means I am going with that decision. And I am going to get $1.44 million written above the decision node number 6. So expected value of decision node number 6 is going to be, again, max of EV of node 9 and 0.7, which is naturally EV of node 9 and is 1.44. Now, look at the chance node number 4. There are two probabilistic events coming out, which is forecast strong and forecast weak, and we found that the probabilities for them are 0.6 and 0.4. So if you're interested in finding, let's say, if you're interested in finding the EV of chance node, the EV of chance node 4, right at the moment after selecting and paying for market research, that is going to be 0.6, which is the probability of a strong forecast, times the outcome of that, $2.34 million on average, and then 0.4, the probability that the market research will forecast weak, and then the outcome would be 1.44. Okay, so we can compute that as well. It's going to be this number. So it's going to be 4 and then 0 and then 1.4. So it will be 1.404. And then the next part is going to be 6, 7, and 5. 0.576. And when you add these numbers together, what you're gonna get will be 0, and then 8, and 9. 1. So 1.98. Okay, so $1.98 million is the EV of node 4. I'm gonna write it here in red color. So let me just remove these things. Okay, so EV of node 4 is $1.98 million. Okay, so what is the next step then in this process? $1.98 million. That's note 4. So we have to also do this process for the scenario of no market research and then the EV of node 10 as a result. So let's do that. Is the last one we need to do effectively. EV of node 10 is 0.6 the prior or outdated or unconditional probability of high demand times 2.8 and then plus 0.4 over here, the weak demand times 1. The outcome is $1 million. Okay, so we get 8 and then we get 1.68 and then for the other one we get 0.4. So the outcome is just $2.08 million for EV of node 10. So I am going to write it there. For node 10, I am getting 2.08. And you can already see that at decision node 7, if we build the product, we're going to get 2.08 on average expected value. And if we sell the product, we're going to get 0.8. So forgetting about risk, which is not a concern at this point in this problem. So we're going to go with the 2.08. So above node 7, I'm going to write 2.08, which is the backward pass-through expected value. And we're going to build the product. So no matter if we do market research or not, we're going to build the product. And you can see that actually if we don't pay the market research and just proceed with no market research, we get on average expected value 2.08. If we do market research, we're going to get 1.98. So that's very interesting. Obviously, based on this outcome at decision node number 3, we are not going to pay for this market research because without paying, we are better off. So I would say that here the expected value of node 3 is the maximum of EVs of node 4 and EV of node 7, which as a result you can see that it will be EV of node 7, which is 2.08. So I'm gonna write here 2.08, and it means don't do market research, just proceed with the whole thing. And of course, when you get 2.08, then probability of win is 0.75, probability of losing is 0.25. So the last thing we need to do on this decision tree is the nice step of finding the EV of node 2, which is 0.75, this probability, times 2.08 plus 0.25, losing, times negative 0.2 as a result of losing, which we can compute, and that would be the EV of node 2, which is effectively the expected value that we're going to get from this project, basically, because that's the last one, EV of node 2. Of course, this EV of node 2, you can already see that it would be a positive number. I mean, when you compute it, whatever number it is. And because it's a positive number, the bidding result has a positive outcome, while the no bidding result has a 0 outcome. So obviously the decision would be, we will be bid as long as, like this example, the EV of node 2 is positive. So basically the summary is, yes, given the numbers we saw here and application of Bayes theorem, we are going to bid on this project. We're going to pay the cost of $200,000 for bidding. And then when we win the contract, then we don't do the market research. It's useless for us. And when we don't do the market research, we proceed and we actually build the product, because building it gives us on average better outcome than selling the IP. So that's what the recommendation will be for the management. And if somebody comes back and say, hey, can we negotiate with the market research company and reduce the cost? What is the right cost? We would say it doesn't make sense, because right now the delta between 2.08, the payoff without market research, and 1.98, the payoff with market research, is actually the delta of $100,000. So they actually should do market research at no cost, because already cost is 100K. If they do zero, then that would exactly offset the delta between these two scenarios, with the zero meaning that instead of $100,000 cost of market research, if it comes free, then 1.98 will become 2.08. And even with the $0 market research cost, the outcome or payoff of a market research scenario will be just equal to the no market research scenario. Then it's on par, and maybe because of the fact that there might be some other information available, then it might just make sense that we proceed with market research, but barely, so they are just on par. Okay, so I hope that this example of a decision tree for the product management example, with including application of Bayes theorem to update the unconditional prior outdated probabilities into revised and posterior probabilities as I did, and then finding the EV of different nodes and doing the backward pass through the decision tree for the expected values to find the expected value of overall decision tree and then the best recommendation. I hope that this whole thing has been insightful and helpful.